So we've seen the definition of integrals via limits of Riemann sums as we refine partitions and so on. Obviously, we don't want to start calculating volumes of undergraphs of two-variable functions using Riemann sums. We've seen a whole bunch of theorems that tell us many observations. We didn't prove almost anything, but kind of make observations about double integrals and help us stabilize the intuition and feel good about double integrals. But none of these theorems tells us how to calculate a double integral. And here's the theorem that does. And we're going to state it first in this clip only for very simple situations, namely continuous functions defined on rectangles. And we're going to see later how to generalize it a bit. So here's the theorem. Let D be a rectangle. Remember, we denoted a rectangle by AB cross CD. Remember this? So this means the Cartesian product, all the points x, y, such that x is between A and B, and y is between C and D. Remember this notation? So let D be a rectangle. And let F be continuous on D. Then, can you sound the trumpets, please? Here it comes. Ready? The double integral over D of fxy dx dy equals, let's take a short 5-minute break for commercials. No, just kidding. Equals, here goes, the integral from A to B dx of the integral from C to D dy of fxy. So what did I just write here? These are regular single variable integrals. I'm taking the function f of xy and regarding x as fixed, as a parameter, fixing x. And inside these parentheses here, x is fixed, so f is a function of y alone. I'm integrating single variable, single snake, between c and d, f as a function of y, integral dy. Do you see that this is something you know how to do? We'll do an example in a minute. The result is going to be a number, right? The integral of a function is a number. It's the area under a graph, right? But this number depends on what x was. For every x, we're going to get a different number here. Do you agree? So in fact, this entire inner thing is not a number. It's a function of x. For every x between A and B, it's a different number, right? So that function of x, we're going to integrate from A to B, dx. This is called iterated integrals. We're breaking the double integral into two iterated single variable integrals. Okay? Now I want to remind you that back when we discussed limits, we said never do iterated limits. Iterated limits are a big no-no. They just don't do what you want. Remember that discussion? But for double integrals, it turns out that this is the basic theorem. This is how we calculate integrals. And it is via this notion of iterated integrals. It requires proof. I'm just going to mention the idea. I'm not going to write a formal proof. But for integrals, the notion of iterated integrals is very important and very useful. Okay? So despite the fact that for limits it's a non-notion, it does exist, but it's usually more confusing than helpful. For integrals, it is good. And note that integrals are limits, right? Integrals, by definitions, are limits of Riemann sums. Okay, they are limits in nature. And nevertheless, this is the right notion. Let's do an example. Let's see how we use this in an actual simple example so you can appreciate that this really tells you how to calculate a double integral. Okay? So here's an example. Let's look at the function fxy is just going to be x times y. It's the first example, so it's an easy example. And let's take the domain D, the rectangle, is going to be 1, 2 cross pi over 4, pi over 3. Okay, so this is the domain, all the xy's such that x is between 1 and 2, and y is between pi over 4 and pi over 3, right? That's what's written here. And the function is just f of xy equals x times y. What is the double integral over D of xy? By the theorem, we have to take the integral from 1 to 2 dx of the integral from pi over 4 to pi over 3 dy of our function x, y. That's the theorem we just wrote down. Do you agree? Everybody? Now, how do we calculate this? We always start from the inner integral and work our way out. I'm saying work our way out and doing this because now we're doing 2 snakes, but later we're going to do 3 snakes. Okay, and there's no reason not to do 4 and 5 and 6 snakes except it gets long. Okay, so you always start from the inside and work your way out. Looking at this inner thing, ignoring the integral from 1 to 2 dx, just the inside, x is fixed. I'm only integrating dy. So this equals, I'm leaving the outer integral untouched for a minute. How do I do an integral of xy dy? Calc 1. Okay, I'm back to Calc 1. Whether that's good news or bad news depends on how well you remember how to calculate integrals in Calc 1. But basically, every snake that's going to show up on the board in this course, at the end is going to be evaluated using Calc 1. Okay, so you have to remember those Calc 1 tools, such as integration by parts and just straightforward antiderivatives and substitutions and everything. You have to remember how to do those things. Okay? I hope I didn't break anybody's heart now. Everybody, I broke your heart. Sorry. But it's okay. It's okay. It's fun. It becomes fun. No, come on, smile. Good. Okay. So what's the antiderivative of xy? X is fixed, right? So it's xy squared over 2. That's the antiderivative, evaluated between y equals pi over 4 and y equals pi over 3. Do you agree that I just solved the inner integral regarding x as fixed? It's the anti-process of taking partial derivatives. Clear? So what do I get? When I plug in, so I get the integral from 1 to 2 of x dx. And when I plug in the values for y, I just get numbers which I can pull out of the snake, right? So I get, what do I get out here? I get pi over 3 squared over 2. So let's write it 1/2 pi over 3 squared minus pi over 4 squared. Do you agree? Everybody with me? Say yes. Come on. Okay. Equals. What's the integral from 1 to 2 of x? Let's move this up a bit so I have room here. So I have x squared divided by 2, evaluated between 1 and 2, that's this integral, times, I have here 1/2, and I have here pi squared over 9 minus pi squared over 16. Do you agree? Okay. When I plug in 2 here, I'm going to get 4 over 2. So let's pull out a pi squared here. So pi squared over 2. I have 1 over 9 minus 1 over 16. Let's do the common denominator in the next step. And from here I have 2 squared, which is 4 over 2, which is 2, minus 1 squared, which is 1 over 2. So I have 2 minus 1/2. Do you agree? Okay. And this, you can do a common denominator. It's going to be what? They don't have common factors, so it's going to be 90 plus 54. It's going to be 144. 16 minus 9 is what? 7. So this is 7 over 144. This is 7 over 144. This thing is 3 over 2. And then things probably cancel out a bit, or not. They don't. This has a 3 factor in it, right? So this 3 is going to cancel with this, leaving us with, what, 48, right? So it's 7 pi squared divided by 48 times 4. That's it. 192. Do you agree? What you should notice is the following. 1, after you do the inner integral, there should be no y's. 2, after you do the outer integral, there should be no variables at all. You should get a number. A double integral is a number. Clear? Okay, so that's important. And you should also notice here we didn't do anything sophisticated. We didn't do any substitution or integration by parts or anything. These were just completely immediate integrals, okay? But you should notice that what we're doing, in fact, is evaluating single variable integrals. That's what this theorem tells you. Good? Everybody? Okay. So in the next clip, what I want to discuss is how to generalize this theorem. Okay, so this theorem was only good for very restrictive conditions. D has to be a rectangle. That's a big restriction. And F has to be continuous. Well, that's not too bad. Okay? And generalizing it, we're going to discuss that in the next clip. I just want to mention, I'm not going to do the proof of this theorem, but the idea of the proof is just replacing all these integrals with sums and doing the summation. So the double sum you can write as a sum of sums. Right? A double sum, the sum over I, the sum over j, those were the Riemann sums. It's just a sum of sums, and then you can take argue that you can take the limits in an iterated way. It's kind of, that's just the idea. It's not a proof. Okay. So that's the end of this one. In the next clip, we're going to generalize this to a more general condition than just rectangles. Coming up next.